Very good, very good afternoon to all. Today's speaker, respected Dr. Sivaprakash Sengodan, Imperial College Research Fellow, Department of Materials, Imperial College London, and our beloved principal, Dr. S. Selvan, and our coordinators, Ms. J. Shiba and Mr. P. Arvind, and dear participants from various academic institutions, industries, and research institutions, and my dear colleagues. It gives me a great pleasure to welcome on my own behalf and our institute behalf, Dr. Sivaprakash Sengodan to deliver a valuable lecture in the second session of our faculty development program on advanced technologies in chemical industries, organized by the Department of Chemical Engineering, St. Peter's College of Engineering and Technology, in association with professional bodies, Indian Institute of Chemical Engineers, SPCT Student Chapter. A warm welcome to all our participants from various institutions. I hope this session would be more interesting and informative to all the participants. With this, I request coordinator, Ms. Shiba, to introduce our speaker, Dr. Sivaprakash Sengodan.
Thank you, sir. Dr. Sivaprakash Sengodan is currently working as an Imperial College Research Fellow in the Department of Materials, London. He has completed his MTech at Anna University, finished his PhD in Energy Engineering from Ulsan National Institute of Science and Technology, Korea. Later on, he continued to do his postdoctoral research associate in a School of Engineering at University of Warwick. His research areas are development of electrode and electrolyte materials for energy conversion and storage devices, especially for solid oxide fuel cells, protonic ceramic fuel cells, and metal lab batteries. Now I request a distinguished speaker to carry on with this session.
Thank you for this introduction.
Sivaprakash, sorry for the interruption. Your mic is muted, sir. Kindly unmute it, sir. Thank you,
sorry,
sir.
Sorry. Okay. Thank you for the kind introduction, and then I'm very thank you for the panel members for inviting me for this lecture. Today I'm going to share about my experience in the development of electrolyte materials in solid oxide fuel cells. So my title is on all around applications of layered perovskite materials in solid oxide fuel cells. So my talk goes with this content: introduction, status of the fuel cell all around the world, and then the development of solid oxide fuel cells, perovskite cathode, perovskite anodes, and then other applications of layered perovskite. Due to time restriction, I'm not going to cover on that, and then a small conclusion on that. So why we need to develop a fuel cell? Because currently the power is centralized. Because of this, there is a huge cost, and then danger is going on there in the nuclear power industries. It's hiding my window. And then due to the centralized power, there is a high chance of blackout, and then there is a high social conflict between the urban and then the rural areas in the power generation and then distribution. Along with that, the transmission and distribution loss factor is also very huge, about 4 to 11% from the energy generation electricity produced at the power plant from thermal or solar power plants, and then transmitted to the household. It takes about 4 to 11% of loss factor. So this is the reason why we need to develop a distributed power generation Here in Masdar city and UAE, they developed a off-grid, which was not connected to the central power transmission. It was connected with the localized power. And then the second advantage is the construction of a localized power unit. It takes very few time, like within 1 year time frame, we can construct a megawatt power densities unit plant. However, construction of a thermal power plant or a nuclear power plant, it takes about 5 to 10 years. Again, the localized power generation example, for example, fuel cell is can be combined with the other power generation techniques or technologies, including solar, wind, geothermal. And then since energy is produced at localized power, and it is a green energy, it will not have any adverse or negative impact on the global environment. So there are a variety of fuel cell choices are available, but including the polymer electrolyte membrane fuel cell, which operates at 70 degrees Celsius, phosphoric acid fuel cells, which operate about 200 degrees Celsius, molten carbonate fuel cell, which operates about 600 degrees Celsius. Solid oxide fuel cells work on above 800 degrees Celsius to 1000 degrees Celsius. But along with important thing is solid oxide fuel cells can cover the whole range from mobile application to the stationary power plants. Types of fuel cells. There are various types of fuel cells there. It was classified based on their operating temperature. Solid oxide fuel cells work at 700 to 1000 degrees Celsius. And then the main difference is the electrolyte material. Here the zirconia, stabilized zirconia or a ceramic membrane is used as a electrolyte, which is efficiency source about 45 to 65%. Only the power self efficiency when we combined with the heat turbine engines and capture the waste heat, the efficiency can be moved over 90%. The second type of fuel cell is the molten carbonate fuel cells, which operates about 650 degrees Celsius. The electrolyte is molten carbonate, and then efficiency is only about 45 to 50%. Phosphoric acid fuel cells works at 200 degrees Celsius, and then the electrolyte material is phosphoric acid, and then power generation efficiency is 35 to 42%. The third one is that the fourth one is that polymer electrolyte PEM, we simply call as polymer electrolyte membrane fuel cells or PEM fuel cells, which works on the ion exchange membrane known as for example, on the Nafion membrane, and the efficiency about 35 to 40%. Based on the electrolyte materials, we can use different type of fuels for the fuel cells. Among all the fuel cells, stabilized zirconia is an oxide ion conductor, where we can basically put any type of carbon fuels or hydrocarbon fuels or hydrogen. Whereas in ion exchange membrane, we can only put a pure hydrogen, about 99.9% hydrogen as the fuel. But in solid oxide fuel cells, we can basically give all the carbon or hydrocarbon fuels where it may contain sulfur containing or other contaminants. So application of fuel cells are widely used. The application fuel cells ranges from stationary power to a mobile power and then portable power. For example, here at US, the Bloom Energy is a first company where they started commercializing the solid oxide fuel cells, and then it was installed in many corporate offices, including Google, Tesla, everywhere. And then the mobile type fuel cells are mainly used in electric vehicles, combined electric vehicles in powered cars. They mainly use the polymer electrolyte membrane as the ion exchange membrane, and then pure hydrogen as the fuel. And then portable power also, there are startup companies are available now, but still not commercialized. Various status of the fuel cell around the world I'm showing here. Bloom Energy is the first company who commercialized the solid oxide fuel cell technology. Sorry for I put everything in the Korean. I prepared this very long time ago. And then many corporate office, they're having the stationary power unit, fully powered by the solid oxide fuel cells, including all the corporate office tech companies, Google. And then the new new companies on GE, they're working on solid oxide fuel cells, and then they claim that their efficiency is about 95% when waste heat is captured from the heat turbine engines. And then fuel cell energy company, they also installed many fuel cells at different landmarks, including agriculture, landfills, food processing industries, oil and productions. Again, there is another company in UTC Power. They are also having it's supported by the government, and then most of them, they work on with the government power plant, power sectors like a national bank, and then city council, police station, everywhere. It's a startup one. In Japan, KY Sera is another company. They're working on the solid oxide fuel cells with the electrolyte LSGM, gallium magnesium based electrolyte material. This was combined with the home boiler, where we can simultaneously generate the power, and then simultaneously we can heat the home thermostat controlled. In Korea, there is a new company called Miko Corporation. They started to develop a solid oxide fuel cell technology. They now on the stage of preparing the cells, and then their plan is to construct a 5 kilowatts SOC hybrid engine to install in various government sectors, particularly in the universities. So I'm going to give an overall introduction about solid oxide fuel cell, basic principles on solid oxide fuel cells. Solid oxide fuel cells are electrochemical reactor which converts chemical energy directly into electrical energy. Like other type of fuel cells, solid oxide fuel cells have mainly three components. One is the anode, electrolyte, and then the cathode. The anode is mainly composed of nickel and zirconia composite materials, and then electrolyte is mainly composed of stabilized zirconia ceramic membrane, and then cathode is composed of a perovskite materials like lanthanum, strontium, magnesium, lanthanum, strontium, cobalt. So in cathode, first the oxygen is get reduced with the electron, and then moves towards the anode through the electrolyte, and then in the anode, hydrogen reacts with the reduced oxygen to form the water, and then power is generated in the external circuit. Water is formed in the anode compartment. Whereas many people are familiar with the polymer electrolyte membrane fuel cells. In polymer electrolyte membrane fuel cells, oxygen is get reduced in the cathode, and then the fuel is get oxidized and then moves towards the cathode, and then water is formed in the cathode compartment. Whereas in solid oxide fuel cells, oxygen ion is conducting from the cathode to the anode. Because of this reason, water is formed at the anode compartment. And another advantage of this zirconia membrane is, since oxygen ion is moving here, we can basically put other hydrocarbons like methane. It can be easily combusted, and then power is generated. When methane is the fuel, carbon dioxide and water is formed as the byproduct in a clean, efficient way, and then power is generated. The main advantages of the solid oxide fuel cells are direct conversion of the fuel into electricity, high efficiency, as I said before, environmental friendly, fuel flexibility. As I said before, hydrogen, hydrocarbons, even carbon fuels, solid carbon fuels can be used as a fuel in solid oxide fuel cells. The main disadvantage is the performance degradation, and then the high thermal stress interfaces of the components. Performance, since the fuel cell is operating above 800 degrees Celsius, typically at 1000 degrees Celsius, the fuel cell components undergo corrosion, severe corrosion. This is the main disadvantage. Because of this severe corrosion, performance degradation happening, and then due to the performance degradation, stress is built on the interfaces between the anode and the electrodes. So the main research is going on in solid oxide fuel cell is reducing the operating temperature to 500 to 700 degrees Celsius, so that we can stabilize the cathode without any degradation. And then the main another disadvantage in reducing the temperature is when reducing the temperature, the catalytic oxygen reduction activity here this goes down. When temperature is high, oxygen reduction ORR will be very high. That's very rate limiting step. When decreasing the temperature, that oxygen reduction reaction undergoes degradation, and then this rate limiting step is also higher. So next I will introduce the components of solid oxide fuel cells, the electrode materials used in solid oxide fuel cells. In solid oxide fuel cells, mainly simple perovskite is used as the electrode materials, such as barium, BSCF. I will explain in the next slides what is BSCF, LSCF, everything. BSCF, LSCF is used in the fuel cells. In metal air batteries, same as the for oxygen reduction reactions and evaluation reaction, lanthanum strontium cobalt material or lanthanum strontium magnite or barium strontium cobalt ion is used as the electrode material. And then organic perovskites are used in the solar cells. What is the advantage of simple perovskite to the layered perovskites? Compared to simple perovskite, layered perovskite shows the high oxide ion conductivity, fast oxygen diffusion, surface exchange kinetics, and excellent durability. So high conduction gives a fast conduction of oxygen ion, fast oxygen exchange diffusion, surface exchange coefficient improves the oxygen reduction reaction when even we decrease the operating temperature of the fuel cell at the cathode, and it shows excellent durability. Durability is there will be no degradation even for maintaining over 3,000 or 6,000 hours operating the fuel cell. So simple perovskite structure is shown here, and then general formula is shown here AbO3, where A is the lanthanide series elements, B is the transition metal, O is oxygen, and then delta is the oxygen vacancy. Here you can see that lanthanide series elements are on the few corners of the cube, and then in the center of the cube it is the transition metal. Oxygen is present on the octahedral sides, and then oxygen vacancy is present here. So this vacancy is basically that gives the conduction mechanism to move the oxygen from one side to another side. So the various examples of simple perovskites are shown, I given here. Barium, strontium, cobalt ion. So barium is here is A side, and strontium is also A side substituted, and then cobalt ion is the transition metal in B side. So here lanthanum, strontium, cobalt ion is the lanthanide side is A side, and then cobalt ion is the transition metal. So doping here lanthanum is the 3 oxidation state of lanthanum is 3+, and the strontium oxidation state is 2+. So doping a lower valence state in A side, here in the A side within the lanthanum side, create the oxygen vacancy, which is the main path for oxygen ion conduction here. As I explained before, I shown here the simple perovskite structure. These are the A side, and here is the transition metal B side, and then oxygen are present on the octahedral sides. So how we can visualize the double perovskite is when we start doping higher radius in A side. For example, in lanthanum side, we start doping a larger radius barium. In A side, it changes its structure from a simple perovskite to a layered perovskite structure. Here you can show that these are the barium, these are the lanthanum series, and then transition metal. Because of this, the layered structures are formed. In one layer here, only a barium is present, and then here lanthanum is present, barium is present, lanthanum is present here. Because of this reason, we call this as the layered perovskite material. This formed because of the main size difference between the barium and then the lanthanum cations. Here is the unit cell where we can see the double perovskite. And then I will go for the electrode requirements. So a good electrode needs, it should be a catalytically active to allow the operating at low temperature for oxygen reduction reactions, enhance the active sites at the density. And so in the case of anode, it should be catalytically active for hydrogen oxidation or fuel oxidation reactions. Second condition, second requirement is it should be highly ionically conductive. Should for electron transport, at the same time it should be ionically conductive for oxygen ion transport. And then fourth condition requirement is material should be compatible with other components of the fuel cells. For example, if we use a different thermal expansion coefficient having two different materials, anode and then electrolyte, due to the thermal expansion coefficient, different thermal expansion coefficient after sintering or after fabricating the fuel cell, anode and then electrolyte detached from its from their interface. So the material should be compatible with other components, so that there will be a low interfacial resistance. So next I will talk about the solid oxide fuel cell development of solid oxide fuel cell cathodes. Before going to that, I will just give a small brief introduction about how fuel cells are fabricated. So fuel cells are conventionally fabricated by pressing or tape casting methods. For this, we need first, this is the anode material, or the green color is the anode material, nickel and then zirconia, mixed or a composite material, and then tape casted, and then the second layer, this yellow layer is the electrolyte material, this yttria stabilized zirconia. It's tape casted and then deposited, and then the third layer is the cathode, deposited by screen printing or spray coating methods, and then sintering at 1500 degrees Celsius. We can get a fuel cell like here is a finished fuel cells. This one is before sintering. These two types are, the figure shows the before sintering. After sintering, the fuel cell looks like this. Conventionally in laboratory, we do the testing like as I shown here. This fuel cell is placed inside the tube, the aluminum tube, and then electrical connections are made with a silver or platinum wire, and then fuel is purged in the anode compartment, and then the cathode compartment, oxygen is purged. Here I showed the stacking, how they stacked, and then the fuel cell stacks are made for the kilowatt power generation. So in conventional cathode, where barium, strontium, BSCF or LSCF or LSM materials are used as the cathode, the main disadvantage in conventional cathode is the oxygen reduction reaction is very sluggish, or it is very slow. So the conventional fuel cell operate at 1000 degrees Celsius. When we decreasing the operating temperature, this oxygen reduction reaction become very slow. Because of this reason, the overall efficiency of the fuel cell goes down. So we need to find a better cathode which works, which should work this oxygen reduction reaction very good at lower temperature between 700 degrees to 800 degrees Celsius. So in this, first we have developed a layered perovskite material, prismidium, barium, cobalt oxide, the layered perovskite material. This material shows the high oxygen diffusion and then surface exchange coefficient. D and K is D is the oxygen diffusion, K is the surface exchange coefficient. It has a high oxygen transport kinetics. Doping little strontium in the BR site will increases the conductivity and the catalytic activity of the layered perovskite. But doing this, there is a disadvantages. There will be having a large thermal expansion coefficient, poor stability, and high cost. Due to this, then we started working on replacing the cobalt with the iron, so that the thermal expansion coefficient will be matched. It shows a high electrical conductivity. Although it decreases the electrical conductivity, but it is still enough to have a current collection in the fuel cells. The second advantage is that the oxygen diffusion and oxygen reduction reaction stability was increased by doping iron in the cobalt side. Then we found that the prismidium, barium, strontium, cobalt as an active cathode material for solid oxide fuel cells. So based on this fabrication, we fabricated the fuel cells with ceria as the electrolyte. Instead of stabilized zirconia, we used stabilized ceria as the electrolyte, and then nickel as the anode, and then prismidium, barium, strontium, cobalt, iron as the cathode material. And then we performed the fuel cell test at 650 degrees Celsius. It shows about 3 watts power density. And then at low temperature, about 500 degrees Celsius, it's about 0.5 watts power density. Next we check the performance or stability of this material. This prismidium, barium, strontium, cobalt, or iron oxide shows as very stable performance about over 100 hours. But whereas without iron, it shows a sharp degradation. The simple perovskite BSCF also shows a sharp degradation when decreasing the temperature of the fuel cell. Then we started working on the layered perovskite materials to use as the anode material in solid oxide fuel cells. And then we found that prismidium, barium, mangan oxide as a very good electrode material, anode material for solid oxide fuel cells. So why we need to then, there is a question arises, why we need to develop a solid, good anode for solid oxide fuel cells, although there are very active nickel material is available. This is the answer. In conventional fuel cells, hydrogen is used as a fuel. This hydrogen is produced externally by hydrocarbon reforming, or this can be hydrocarbon can directly fed into the fuel cells where it needed a reforming, internal or external reforming. Because of this, there will be efficiency of the fuel cell is decreased by 30%. But using pure hydrogen means it's very hard to produce and then expensive, and then we don't have a good infrastructure to transport the hydrogen. What then the next available is the hydrocarbon fuels. Can we use the hydrocarbon fuels directly? Then for this we need an existing infrastructure. We can use our existing infrastructure, the pipelines or gas cylinders. And then the second advantage is hydrocarbon fuel cells. We have experience in transporting the hydrocarbon fuels like LPG or methane or propane. And then additional processing such as reforming can be reduced. So if the external reforming or internal reforming, if reduced, means this efficiency can be increased. Again, another advantage of using hydrocarbon fuel means it shows it is very efficient, high efficient, cheap and useful fuels. We can use the hydrocarbon, LPG, methane, propane, octane, ethanol, even solid carbon. But what is the disadvantage of the using nickel as the anode material? The conventional anode material is the nickel, stabilized zirconia as used as the anode. It's a composite material, nickel and then stabilized zirconia, the ball mill, and then in different 30-40 ratios, and then ball mill, and then the anode is fabricated. It shows the high electronic conductivity, excellent activity for clean reforming fuels, that is pure hydrogen, chemically and physically compatible with the zirconia electrolyte. It is very compatible with, it will not react with the other fuel cell components. But when we use the hydrocarbon as the fuel, it undergoes severe degradation because nickel is very good, nickel forms a very nickel is very good carbon catalyst, so that carbon fiber is formed on the nickel material. This carbon fiber eventually breaks the fuel cell at certain point, even for within 1 or 2 hours operation. And then second disadvantages is we start with the nickel oxide as the electrode material in nickel cermet anode, and then once we start operating the fuel cell, nickel oxide is converted to metallic nickel. In metallic nickel, fuel cell is operated. Once the fuel we decided to stop the fuel cell and then shut down the fuel cell, and then nickel is again converted back to the nickel oxides. Because of this reason, this nickel oxide converted to nickel and then nickel oxide, there is a huge volume change occurs in the fuel cell anode. This volume change eventually breaks the fuel cell. So if you use the nickel as an anode material, then we have to continuously keep running the fuel cell. Even when we decide to stop the fuel cell, we cannot. Otherwise, the cell will break. So when we start using the alternative fuel cell, the direct hydrocarbon fuel cell anode, where nickel is not present, we use a different electrode material, where when there is a fuel depletion, we can stop the fuel cell and then we can start running again. The second disadvantage of using nickel as a anode material is it's very sensitive to sulfur containing fuels. For example, a hydrocarbon, natural gas, or geothermal gases we use when we using in the anode, there will be a lot of impurity in sulfur containing impurities. Even a 1 ppm sulfur present in the fuel, this metallic nickel degrades very quickly, even for 1 ppm. But in the natural gas, the ppm level is more than 50 ppm. So when we start using the alternative anode materials, removing the nickel to another anode material, we can use the high sulfur content fuels. And then the third disadvantage is the sulfur reoxidation, or we say is the redox stabilization. So there is an immediate need to develop a new anode material where we can use the hydrocarbon as a fuel and then sulfur containing fuel as a fuel, and then we can use redox stability. See, a good fuel cell anode material should be compatible with the other fuel cell components. It should be thermal. It should be compatible with the other fuel cell components like electrolyte. It matches with the thermal expansion coefficient with the electrolyte. It should be catalytically active for fuel oxidation in hydrocarbon. It should be highly conductive to conduct the electrons from external anode to the cathode. It should show a good carbon tolerance and then sulfur poisoning tolerance. So based on this this requirement, I have developed a new anode material, prismidium barium mangan oxide, as the alternative anode materials for solid oxide fuel cells. So it shows a very good structural property, and then it shows the high electrical conductivity, about 10 Siemens per centimeter square in hydrogen at 5% hydrogen. These are the other alternative anode materials. That is the lanthanum, strontium, chromium mangan oxide. It shows about 1 Siemens per centimeter square. It shows up, and then the another double perovskite material, SMMO. This is strontium, magnesium molybdenum oxide, shows about 5 Siemens per centimeter square in 5% hydrogen at 800 degrees Celsius. But my material is in hydrogen. It shows about 10 Siemens per centimeter square in 5% hydrogen. And it is also redox stable. It shows a very good cell performance in hydrogen containing fuels. Here it shows the power density in hydrogen. It shows about at 800 degrees Celsius, it shows about 1.7 watts power density in hydrogen. In propane, it shows about 1.2 watts power density in propane at 800 degrees Celsius. And then the stability is also very good, which does not show any degradation more than 500 hours in carbon containing fuel, in carbon containing fuels. Whereas if I use the nickel containing electrode material, degradation will be very, very quick. Even within 1 hour, it goes down. So here I showed how I prepare the layered perovskite material. To prepare the layered perovskite material, first I prepared a prismidium barium manganese simple perovskite materials. When this simple perovskite material is kept under reducing conditions at 400 degrees Celsius, it undergoes a spontaneous phase transition. Here, from simple perovskite to layered perovskite structure is formed. And then here shows the XRDs of the XRD peak of the layered perovskite, simple perovskite material. And then this is the layered perovskite material XRD. As I shown before, this shows the high electrical conductivity, 10 Siemens per centimeter square, and then high performance at 850 degrees Celsius in hydrogen, very stable performance in hydrocarbon containing fuels. So in conclusion, the cell performance shows that without any degradation, high electrical conductivity was achieved, excellent redox properties achieved, good carbon coking tolerance achieved from this data. This shows the performance of praseodymium barium mangan oxide. In hydrogen, it shows a very stable performance. But when switches the fuel from hydrogen to 30 ppm sulfur containing fuel, still it's stable. There is no degradation observed, substantial degradation, but it's 1% degradation is allowed in the fuel cell technology. So other applications of layered perovskites are symmetrical solid oxide fuel cells. So in symmetrical solid oxide fuel cells, advantages is easy to fabricate, minimum compatibility problem, elimination of sulfur, and then coke formation. So in solid oxide fuel cells, before I showed that cathode is a different material, electrolyte is a different material, and the anode is a different material. In symmetrical solid oxide fuel cell, the concept is using anode and the cathode as the same material. For example, material A used as a used as anode, same material B, same material A is used as the cathode here also. So when we start purging, when we use the hydrogen or hydrocarbon as the fuel, even though the carbon is deposited on this side, then we can switch the fuel from anode's compartment to the cathode compartment, so that the deposited carbon is exposed to the oxygen containing atmosphere. This deposited carbon will be oxidized to carbon dioxide. So here then the fuel cell is reversed. The reaction is in this way. When switching the fuel from anode to the cathode compartment, the reaction flows in the opposite directions. Similarly, when sulfur containing fuel is exposed to the anode, there will be a degradation. So when we start purging when we stop the sulfur containing fuels and switches from anode compartment to the cathode compartment, the sulfur deposited and the anode materials will be converted to sulfur dioxide or sulfur oxide, other materials, other sulfur oxidized product, when we expose this to the oxygen, so that the cell will be continuously without any stopping or without any interruption. The cell will be keep running. The main requirement is that it should be good structural stability and high conductivity over wide range of oxygen partial pressure. For example, we start using the hydrogen in the anode compartment. The electrical conductivity is decreased, but in the same material in the cathode compartment, the electrical conductivity will be higher. So when we switch the compartment, switching the fuel from compartment A to B or anode to cathode, it should, again, the cathode here, the electrical conductivity should be high enough to conduct the electrons in the external circuit. And then this second requirement is it should be highly catalytically active towards fuel oxidation and then oxygen reduction reaction. Fuel oxidation is the for oxidizing the fuel from hydrogen to water or methane to water, carbon dioxide. At the same time, this material should be active for oxygen reduction reactions. So based on this requirement, we have developed a praseodymium barium mangan oxide by doping a small amount of calcium in the A side. We developed a symmetrical solid oxide fuel cell where anode and then cathode is the same material. At 800 degrees Celsius, it shows about 1.2 watts power density. In methane, it shows about 0.7 watts power density. In octane, that is the jet fuel. Jet fuel is used in aviation industry, aviation fuel. When we use the aviation fuel, it shows about 0.5 watts power density. In hydrogen, it shows about a stable performance without any degradation over 50 hours. Then we switch it to jet fuels. There is no degradation also. Then we change it to the propane. There is also no degradation. This shows that this layered perovskite material can be used as a symmetrical electrode materials for solid oxide fuel cells. Then now I'm currently working on solid oxide electrolysis, solid oxide cells. This solid oxide cells is a combination of solid oxide fuel cell and solid oxide electrolysis cells. So considering there is a excess power generation, then we need to store the energy. So using solid electrolysis cells, here we can put the we can use water when there is excess power. Use water, and then we can split the water into hydrogen and then oxygen, and then oxygen goes to the air electrode, and then the hydrogen is stored as a fuel. When there is a power depletion, this hydrogen can be fed in the same fuel cell, and then water is produced, and then the power is generated. This concept is like when there is excess power, we can store the energy in the form of hydrogen by converting water into hydrogen in electrolysis mode. When there is a power depletion, the stored oxygen can be used as the fuel for the solid oxide fuel cell mode. So this is the combination of both solid oxide fuel cell and electrolysis cell. So here I showed the SOECs, solid oxide and electrolysis, and then the combination of solid oxide electrolysis cells using prismidium, barium, mangan oxide as the electrode material, the fuel electrode. And in fuel cell, in electrolysis mode, the current density is about 1.5 watts, 5 volts per centimeter square, and then in fuel cell mode, we can generate about 2 ampere per centimeter square. Compared to the other literature materials, my material shows a very high current density, about 1.3 ampere per centimeter square. Shows a stable performance over 50 degrees Celsius under fuel cell mode. Here I showed the electrolysis mode and the fuel cell mode. First, in the electrolysis mode, water is fed and then hydrogen is produced. When switching back to the fuel cell mode, hydrogen is used as a fuel and electricity is boosted. By continuously switching for more than 15 hours, there is no degradation. The fuel cell works very good. But there are many other electrode materials are available, like LSM. This LSM in electrolysis mode, there will be an interfacial degradation. In this SEM, you guys can clearly see that there is a due to oxygen buildup, there is a break happening between the electrolyte and the LSM electrode material. Because of this, the interfacial resistance will be very high, and then cell eventually break down. In the second part is that in the fuel electrode, that is the nickel. When hydrogen is purged here, the nickel material is present. When switching to hydrogen to water, that is in the electrolysis mode, this nickel get oxidized to nickel oxide. Because of this, there will be a huge volume change. This volume change eventually break the fuel cell or electrolysis cell. But using the prismidium, barium, strontium, cobalt ion as the fuel electrode, there is no oxygen buildup in the interface between the electrolyte and the electrode. Even in the electrolysis mode, there is no interfacial breakdown, whereas in the LSM material, there is a huge breakdown. In the fuel compartment, when we use the prismidium, barium, manganese oxide as the electrode, even switching from hydrogen to water, there is no structural or volume change. It shows a very stable performance in fuel cell and electrolysis mode. So in conclusion, we developed a layer perovskite material which shows a very high performance in solid oxide fuel cells, symmetric solid oxide fuel cells, combined solid oxide and solid electrolysis cells. I'm not sure, due to time restriction, I didn't show the application of layer perovskite material in protonic ceramic fuel cells and metal air batteries. Thank you.
Any queries? Hello. Any queries?
I think most people don't understand because I'm material scientist. You people are like a chemical engineering, where they do the modeling and then the heat mass transfer.
Shall I conclude?
Yeah, Ganesh.
Oh, okay. I'll conclude. It is my great privilege in proposing this vote of thanks. On my behalf of the management and department, I would like to thank our honorable speaker, Dr. Sivaprakash, on sparing us a time on his busy schedule and giving us a good presentation on recent developments in fuel cells and future of energy engineering. I would thank you, sir. I would like to thank our HOD, Dr. Dinesh Kumar, and all the staff members in organizing this FDP. At the outset, I would like to thank all the participants from various colleges across the country in joining this session. Thank you, everyone. Thank you, sir. Thank you, sir, for giving us a good session and good presentation on future of fuel cells. Thank you, sir. Announcements to all the participants. Tomorrow, the session will be starting at 2:30 p.m. on wastewater treatment. And stay tuned. It will be posted all the announcements in the WhatsApp group. Thank you.
Thank you everyone. Bye-bye.
Thank you.
Thank you, Sivaprakash sir.
Yeah, welcome.
You have given a wonderful presentation and more
Thank you.
informative. And in future also, we will request you to give this kind of presentation, sir.
Yeah, sure.
Thank you so much, sir.
Okay,
Yes,
welcome. Bye-bye.
thank you, sir. Yeah.